So today we're going to be going through what's been coming for a long time, which is a new method for microfluidic PVT analysis, or advanced constant composition, advanced CCE. There's a lot of names for it all over the place. But this work is the culmination of multiple years of development work and validation work in partnership with Equinor, ExxonMobil, and Chevron, as well as many other supporters throughout the PVT ecosystem. And so today we're excited to show off methods as well as data and comparisons to traditional PVT measurement technologies. We'll also be going through new workflows that we are in the process of developing and validating and working with the industry on. So this is going to be a slightly longer webinar than our usual short and sweet ones, but there's a lot to cover. And so if folks need to come in and drop off, please feel free to come in and go. I'm Stuart Kinnair. I'm the CEO and co-founder of Interface. I've got my colleague here, Ali. Ali, would you mind introducing yourself?
Hello, everyone. I'm Ali Obedini, and I'm the Executive VP of Operations at Interface Fluidics. Happy to be here with you guys.
Right. Well, with no further ado, we'll get right into it. So before we get actually into the content, I just want to remind everybody, what is it that Interface does and why do we exist? Interface exists because we believe that there's a fundamental bottleneck in the accessibility of high pressure, high temperature data, whether that is PVT data, chemical performance data, water. Basically, if we're going to put something into our reservoirs to understand those reservoirs, it's really hard to get good information. And we spend a lot of time and a lot of money getting the best possible information. Our goal at Interface is to make those bottlenecks go away as much as possible. And so that's what we have developed all of this technology to really do, is make it accessible. For those of you that don't know, we use a technology at Interface called Microfluidics. Microfluidics is a miniaturization technology. It allows us to miniaturize traditional lab testing technologies. And it was actually first commercialized and first developed in the 1960s, specifically to look at water floods. You can see here, this is one of the first microfluidic papers that was published looking to understand water flood performance. We're measuring fluid flow at the micrometer or nanometer scale. And it requires a lot of specific precision instrumentation in order to actually perform these experiments on the very small volumes of fluids that we use. Interface does high pressure, high temperature fluid analysis in, say, 6 broad categories. Many of those are enhanced recovery, production, or chemical analysis perspectives, like hydraulic fracturing, formation damage, EOR, carbon storage, and flow assurance. But what we're here today to talk about is all the PVT capabilities that we've got. We've developed and validated this technology with a lot of folks over the years. We work with great companies all over the world. So you can take a look at some of the names that we've been working with over the last couple of years. Now, into the meat and potatoes here. PVT lab of the future. It's a big sort of audacious way to talk about it, but we really do think that we can, by thinking differently about what a PVT lab can look like and be, we can start looking at how PVT data delivers value to the industry and how we can optimize that process. So just as an overview, where I'd sort of like to set the stage. Traditional PVT cells deliver exquisite data. I don't think there's anybody within Interface or in the industry that would say that, a really good PVT cell is going to give you very good data. So that's not the problem that we're dealing with here. The problem is that those PVT cells have a lot of baggage. They're bottlenecked. They take large samples. They can take a long time due to the cost of actually acquiring enough PVT cells to deliver market or address market demand. And so really what Interface is trying to solve here is not a data quality problem, though we do address that. It's more of a logistics problem. How do we do more PVT testing with less cost in a more timely manner? And so the problems that we're actually solving at interface with our technology is we reduce the time per measurement anywhere between 10 and 100 times, depending on which kinds of measurements you're making. We use on the order of milliliters of fluid instead of hundreds of milliliters or liters of fluid. Our system is designed to be deployed to where the wellhead is rather than bringing the sample to the lab. So long-term, our goal is, really embody a laboratory to sample mentality rather than the sample to laboratory mentality that has been throughout the industry. In traditional PVT cells, repeatability of the data is often unreported just due to the time and cost and sample requirements. So you don't know, well, how repeatable is my data? By miniaturizing everything, it's much safer. There's much less contained energy. And overall, these are much easier systems to operate for those that do use them. Everything I'll show you today is on our Sapphire Lab hardware that is designed and rated to 15,000 PSI or 1,000 bar and rated to 400 degrees Fahrenheit or 200 degrees Celsius. I mentioned Sapphire Lab before. So this is Sapphire Lab. It is a portable microfluidic system that allows you to make fluid interaction and property measurements where you need to make them. These are the systems we use internally at Interface to make these measurements. They're also the systems that we provide to outside third parties like laboratory companies, oil and gas companies with laboratories, or other service companies that want to be able to deliver our measurements to their clients wherever they need to deliver them. So we'll go through today, the way we'll structure this is we're going to start with routine PVT analysis that's going to cover gas, condensate, black oil, CCE, as well as density and viscosity. We'll then get into some of them more EOR focused or niche focused, like swelling tests, swelling tests and minimum miscibility pressures, as well as following that, the new workflows that we've developed. So on the black oil system, what we're trying to do here, and we've tried to put this into a cartoon to make it easy to understand what you're going to be looking at in the future here. If we've got our phase diagram on the left, and during each measurement, we're starting from reservoir pressure and going down through saturation pressure into the two-phase region. What we have on the microfluidic device is a small slug of oil that as it is isolated and as it experiences that pressure drop at a constant temperature, we see bubble nucleation, we see those grow, and we're able to measure saturation pressure, liquid volume fractions, and relative volumes during that process. We want to see what the raw video here or the raw images of these tests look like. You can see on the left sort of a summary of what the images are going to look like. You can see here the slugs are much larger in real life than they are in that cartoon. So we've got a slug that starts down here and goes all the way up to here. And then we have a second that starts here and is out of the sort of cropped frame. And I'll play a video here that shows as we depressurize the system, we see gas come out. And at each set pressure point, our image analysis algorithm goes through and makes sure that we know how much gas and how much oil. And one note here is oil is always white in all the videos that you're going to see here as we're using fluorescence microscopy. Ali, is there anything you wanted to add on to what folks are looking at here?
No, I think that's pretty much it. Again, as we deplete the pressure further, basically the gas bubbles grow in size, and we are able to quantify the liquid volume, relative volume, and bubble point as a part of this test.
So what we always say at Interface is show, don't tell. So we spent a lot of time running blind validation studies over the last 2 years with our development partners, where they supplied to us oils and gas condensates that were previously measured with known properties and known physical properties. We then developed and ran our measurements, and you can see the result of that comparison here. We have a very strong agreement between, in this case, you can see the saturation pressures. On the left, the ultimate saturation pressures and how they compare to the Sanchez PVT cell that they were all run on. And then on the right is a parity chart comparing our method to theirs with 5% as the dotted line. This was published just last month at ATCE in the paper that we've referenced at the top there. Beyond saturation pressures, if we zoom in again onto one of these slugs, what we can see is we've got a static slug that's been isolated. We're actually measuring the ratios again of liquid to gas. Ellie, do you want to talk a bit about sort of how we actually, we're presenting one data point here. How much data do we actually collect during the process?
Yeah, I mean, again, if you look at the image on the top, consider that the white is oil, and those black basically pixels inside the white basically line is the gas. So again, over time we measure the amount of oil and gas, and we can plot the liquid volume percentage below the bubble point and also the relative volume over the course of the pressure. Again, the liquid volume is basically calculated using the equation of the amount of the liquid divided by the amount of the liquid plus gas, which is a very critical parameter in order to tune the EOS and match the data. And again, the relative volume is the total volume of oil and gas divided by the volume of the oil at bubble point, which is a conventional way of measuring the bubble point as basically the trend of the data changes when the gas comes into play. And the way, if you look at the data on the left side, you see tiny error bands. Although the error bands are tiny, we measure quite a lot of these tests and repeated them quite a lot. Those error bands came from over 10 data points. They either came from separate runs or, as Stuart showed in the previous slide, in each case, we have multiple slugs of the oil. So we can look at those oil slugs and measure either the bubble point or the liquid volume and try to come up with the sensitivity analysis from run to run and draw the standard deviation of the measurements. So which basically in high level, it shows how the measurement is tight and how accurate in terms of a comparison of our data versus the PVT cell data.
Yeah, we've got a good question here coming in from Hanny. With regard to bubble point detection, how is stirring or mechanical energy input into the system? Without such, we might have a supercritical or a subcritical saturation.
That's a really good point. Because we don't have any internal mechanical mixer in these cells compared to the PVT cell, there's a process that's happening called supersaturation. It means that the bubble basically nucleates at pressure lower than the bubble point. And what we do in our test in order to measure the bubble point, we lower the pressure below the bubble point, typically a few hundred PSI below the bubble point, depends on how heavy the oil is. And the moment that the bubbles form, we stop reducing the pressure and then we go up in pressure incrementally again. And then look at what pressure all the bubbles again go back to the solution. So basically the criterion here to measure the bubble point for us is the pressure at which all the nucleates are going back to solution. And that's the bubble point. In that way, we can actually basically overcome the supersaturation effects that happen in this system. But in terms of timeline, it's pretty fast. You can do it in less than basically half an hour. So less than half an hour, you can find your bubble point. Once the bubble point is fixed, then you go down in pressure and then measure the liquid volume at pressures below the bubble point.
Great. I got another question about heavy oil. I'm going to leave that one to the end, just so that we can keep on rolling here. But I'll give a short answer is yes. But there is obviously some nuance to that answer. So we'll keep going and get back to that question at the end. Thank you. For gas condensates, we've also tested with a number of different gas condensates as well as volatile oils. What we're looking at, if I go back to our cartoon here, is a slightly different picture. Obviously, we start single phase gas. At the saturation pressure, we start to see liquid come out. And then we're measuring the liquid inside of that bubble as we go through, and we're able to calculate accurately the liquid dropout volumes as well as rail volumes again. Now, this picture, you'll notice the microscopes, we're using a different type of imaging in our gas condensate so we can see the three phases more easily, because condensates often have a hard time fluorescing. And so we use both fluorescent and bright field images here. So the big difference is we start with gas and we start to see the liquids near the edges of the gas. And I'll play the video here and we can see as we go down, if you focus on this area here, we can see both phases. And I'll play this one more time and I'll direct people to look right at this area here. So we start with one phase and we can see the two phases happen. So by using the same image processing techniques, we're able to get data that looks like this. Elliot, do you want to walk us through what we're looking at here?
Yeah, I mean, on the left side, you look at the liquid dropout volume versus pressure, and basically they're actually identical. And look at the error band in our data again. Again, they're repeated out of multiple slugs through multiple runs. It shows how the data is tight and accurate versus compared with the PVT cell. Again, you see the dew point where basically liquid dropout starts to rise, and then we can measure the maximum liquid dropout, which also is really important whenever it comes to the condensate. And again, over time, you see the retrograde behavior where, again, the condensates go back to solution. And again, on the right side, we can, again, measure the relative volume the way that we measured for the black oil. Just one quick point here. Again, everything relies on the diffusion here. And to some extent, some sort of the dynamic and when basically the phases are moving around a little bit of convection. But because the system is so tiny, the volume that we are dealing are even smaller than the nanoliters, the diffusion is still very active in our system. So we can reach the equilibrium in less than 10 minutes.
Great, thanks. All right. On the viscosity and density side, one of the challenges we were looking at in developing the system was being able to deliver a reliable density viscosity measurement that got around some of the traditional limitations of the devices that are on the market for measuring density. And so what we did is we actually partnered with a company called Phase Sensors in Edmonton, Alberta, who have developed what we believe to be one of the only, if not the only, combined viscosity and density sensor that's on the market. Ali, I'll let you do most of the talking here about this process.
Yep. I think there's just one typo here. The temperature rating is 180, is not 1800.
Oh, yeah,
I guess there is a
zero.
It's just I guess sign for Celsius. Anyways, yeah, the concept here is these sensors, they use crystal quartz resonator, and it's been in the market before. But when you expose this sensor to a media, including any fluid, basically the resonator resonates with different frequency, and then we actually log the frequency of the resonation, and we draw two parameters of the resonation. One is the wavelengths, basically, and the other is the half peak at the max of the peak. So, and then we actually correlate those parameters with density and viscosity. And the measurement is really fast. You need just less than 1 milliliters of the sample. So the cavity that the sensor is located in, it has around 300 microliters sample volume. The measurement time is really fast. It's less than a minute. And it can give you density and viscosity together, which is not in the market. So it's a really good and powerful sensor.
Yeah. This was designed to be a flow-through sensor so that, at interface, we use these as a inline sensor with the CCE that we just showed you. Other folks are looking at using these in line in many other processes. These are very robust tools that are not just lab instruments. They're designed to be used in the field. And then the last thing I'll note here is the density and viscosity ranges. These are sort of standard oil ranges. With recalibration, the sensor can measure all the way down to very, very light gases, as well as higher viscosity oils and other fluids, as long as they are recalibrated. You want to walk through this as well, Ali?
Yeah, so this is a comparison of the density values once we use the sensor against the numbers came from the standard fluids. Just to give you a bit of background here, we calibrate these sensors with a set of standards in order to make a correlation between the sensor readings and the density and viscosity. And once the sensor is calibrated, then we used it for measuring the oil densities and viscosities. And then after that, we again measured the sensor accuracy using another set of standards to ensure that the sensor is not drifted once it's exposed to the oil, or you don't see any other damages. And you still can see that there's a really good match between the reported values and the measured values. And in the industry, so the way that people also report the accuracy of the sensor is based on the standards, not basically the oil, just because the oil is not a very clean sample, and the way and the measurement is actually done by the equipment out. So we're using the same concept that show the accuracy of the density, so we can see a really good match. So the accuracy is around 0.003 gram per cc, with the mean average percentage of 0.3% across the board, which is really good.
Yeah, it's on. I think the quoted error on competing technologies is about twice that. So we're achieving sort of a best in class error values here. And the same principle of calibration and measurement goes for viscosity. So we're using the same process to make sure that we're getting the right data or getting accurate data. And you can see again here, we're achieving plus or minus 5%, which is the industry standard accuracy on viscosity measurements. So with those methods and that tool, the viscosity and density tool, we're able to generate a standard PVT report. We've got a question here about DLE and CVD. Got a whole section all about that. So I'll ask you to just hold on until we get to that point, but it's coming up shortly here. So with interface, what we deliver is sort of what's on the screen here. So on the left here is your conventional CCE that you'd expect to receive from a traditional lab or a traditional tool. With the microfluidic system, what we're able to actually add to that is everything on the right side. So we're measuring liquid and gas volume fractions, as well as measured densities and measured viscosities at every pressure point above the saturation pressure. Typically, these are delivered as one density that then is calculated across the difference there. So you have a measured value all the way. This is going to be recorded. This is being recorded. It'll be posted on our YouTube channel in probably a week or two. So ultimately what you end up with is a more robust data set for each temperature that you measure. And then our standard is between 3 and 5 temperature points. So we end up delivering curves as opposed to points when it comes to your CCE data. So we're delivering, between 3 and 5 times more CCE data as well as the addition of all the measured density and viscosity information. So it's a much larger data set than you would get from a traditional PVT capability. So with that, going into questions around gas injection and EOR, where we're concerned about things like swelling factor or minimum miscibility pressures. So swelling factor is a really important measurement to understand how our gas injection processes go, whether that is like a CO2 EOR project, or just a gas reinjection program for areas where there's no offtake for gas. So the way that this is done is on our microfluidic device. Again, we've got a bit of a cartoon here to help illustrate what's going on. We have gas that's yellow, that's coming in as bubbles inside of isolation fluid. That gas is then engulfed by the live oil at the oil's saturation pressure. And so what we're creating is an oil and gas, a new subsample with oil and gas, with a known volume of each gas and oil. And so really there's two names for this. You could call this a swelling test, but you could also think of this as a recombination process. The same as what you would do typically in a bottle. With a traditional lab, we're now able to on the fly in real time recombine gas and oil. And we'll get into that. That's part of our DL and CVD measurement process. So we'll get into that and how that works. But what we're looking at here, again, we have oil, the large gas slug. In this case, it's an 81% gas mole fraction versus oil. And as we pressurize, you can see we go from two-phase down to single phase. So we get new PSATs as well as your full CCE data set for each slug. And on the chip at any given time, you end up with, dozens to up to 100 slugs on the chip. So you get very, very large data set out of this system. Anything I've missed or you wanted to contribute on there, Ali?
No, all good stuff.
Great. So the data set looks like this, and I will get Ali to walk through exactly what we're looking at here.
Yeah, so again, what we can get is the saturation pressure of when the entire gas dissolves in the oil. So it's on top right, top left. So look at the accuracy versus the PVT cell, and also look at the error bands in our measurement, because we've got multiples of these slugs, and we can measure them independently and come up with the error band, which is really tough whenever you want to do the swelling test using the PVT cell. And again, the right top photo shows the comparison between the swelling factor measured in our microfluidic system versus PVT cell. And the table on the below shows the basically it quantifies the numbers, and look at the deviation again. You're less than 5%, with majority of the points they have under 2 to 1% deviation from the PVT cell. Again, I just want to remind you of the fact that, again, we don't have any error band on these PVT cell data. Again, there could be some deviation to those numbers as well, but the fact that our data is being repeated for multiple times and has such a tight error band, it's really promising.
Excellent. Going even deeper here, we can look at rel volume for each gas fraction, as well as liquid volume for each gas fraction. I put a note at the bottom here for everybody. This is the only slide where the direct comparison between a PVT cell and a microfluidic system is more challenging, because we're working with different exact gas volumes. If you want to see the best comparison, the 60% values is really what the two closest, where we've got about 60.5 and 61% gas fraction. Ali, you want to talk about sort of the measurement here?
Yeah, so again, as a part of the swelling test, people provide CCE related data, including rel volume and the liquid volume. The left is rel volume, again, which is the total amount of gas and oil divided by the amount of the oil at the saturation pressure once the entire gas is dissolved into the oil phase. And on the right side, you can see the liquid volume. Just again, numbers don't match, but look at the 60.4% for PVT cell and 61.2% for microfluidics. There's a really good match. Another interesting point here is you can also look at the change in the nature of the oil and gas mixture, changing from a black oil behavior, which is in basically orange color, going to the near critical, and then finally it goes into a condensate behavior of the final oil and gas mixture. So when it comes to the saturation pressure of the final mixture, either be dew point or bubble point, we can easily measure that. And the other good point here is that you can actually have a much wider mole fraction of gas here. So you literally can basically narrow down the range where your behavior changes from oil to the condensate as you increase the amount of the gas in the oil phase. Again, and the data speaks itself that it's very consistent, and it matches with the actual data when it comes from the PVT cell.
Yeah. Excellent. Thanks, Ali. So had a question about DLE and CVD. I think it's probably on the back of every sort of PVT professional's mind is what are you going to do about all these measurements that we haven't talked about yet? And so what we've been doing is there's actually a lot of literature out there talking about how to do these measurements, or how to calibrate an equation of state using data sets that are not separator tests, DLE, CVD type measurements. One of the challenges on a microfluidic system, removing components is very, very challenging. And so looking for ways to address that. The swelling test, and as I mentioned before, the on-chip recombination is really a big opportunity. So traditional methods like DL and CVD provide data on how it evolves during production in the reservoir and at wellhead and separator conditions. And these measurements are used to tune and optimize your EOS to represent these fluids in different conditions. While it is the traditional method, these destructive measurements are not necessarily required to create these accurate fluid models. And during the process of performing these tests, you have a lot more human interaction and opportunities for error than with a CCE measurement in the PVT cell. So alternatively, equations of state can be tuned using accurate CCE data sets with multiple GORs and the associated compositional, volumetric, and density data. So you end up, rather than tuning your equation of state with a CCE plus destructive testing data set, you end up with a very high resolution CCE at multiple GORs and compositions. So that's been out in the market and been recommended by many folks over the years and been successfully done. The way that this works at interface is we take a sample, whether that is a single phase sample or a separator sample of gas and oil. We'll then take each of those separate phases, separate the phases to measure your GOR if it's a single phase, and then or take the separated phases and measure compositions, densities, and viscosities. So this is well within the traditional workflow already. We then use the on-chip recombination process that I just showed you to create multiple live oil samples. So we get oil plus gas and in a single phase, multiple GORs. We then perform all of the CCE that you would normally get to result with this data set multiplied by however many GORs you do. So you end up with output tables that actually give you what you need to do this tuning. Ali, do you want to make a few comments here? There's lots to talk about. You're muted still.
Yep. So, sorry. So, yeah, exactly. Again, DLE, CVD, they're important because they give information about the VLE for multiple compositions. Again, people can debate that maybe they are not very suitable tests, especially DL, because the compositional path that we have in the reservoir is not exactly what you get in the DLE, but that's been established in the market. And nothing wrong with those, but we got to know that there are some other issues with those destructive tests because the calculation is based on the material balance that you have to do at each pressure step. And as you increase the number of pressure steps, you basically enlarge the error coming from the material balance. Of course, the advanced PVT cells made it much easier, but I'm sure the old DL or CVD data, they're more erroneous. But here, the good piece here, we don't need to deal with the material balance because, as we showed in those cartoons, we can recombine the gas and oil at any GOR independently, and then you can run the CCE on each of those recombined slugs and then get the VLE data. And ideally for EOS tuning, you need composition data, you need liquid vapor equilibrium data, and you need density, and we can provide all of these information. And on the density side and composition, because we know the initial composition of the oil and gas, and we know the amount of each of them, that at any ratio that we recombine them and reach the single phase, you can easily calculate the composition and also the density, because you know the density of each component and you know the final volume is just the mass divided by the new volume of the single phase. So, and it will almost give the same data set that we need to tune the EOS for multiple compositional paths. And yeah, so this is something that we are trying to test the workflow with some people out.
Yeah. I see another question coming in here that I'll get to in just a moment here. So the last, basically you can then, if you really want to know there's a lot of reasons why you might want some of these destructive tests. You now have a tuned equation of state that can create these tables for you and inject all of that data into your simulation software, into any of your other process engineering software that you require. So overall, this new method that we're describing here retains all the multi-composition element measurements that are required during the destructive tests, but eliminates the compound errors associated with that traditional testing due to the fact that there is no change in mass balance measurements at each pressure step. And it also eliminates any of the subsampling errors that can happen. We can use this to tune as well during production to tune fluid models. One of the best cases we've seen so far is taking the ability to put this device near the wellhead, take separator samples of oil and gas, and recharacterize your PVT very, very quickly during production, which is not something that is typically done because of just the challenge of doing these measurements. And then the beauty is that this data set is directly compatible with the current workflows that all E&Ps use, with full transparency back to your raw data. So if you ever have a question of how did we get to this number, it's very easy to understand exactly where that all came from. So I got a few questions in here that I'm going to get to before I get into miscibility, because we presented that material and work in the past. We have a few things at the end that I'll share that are kind of new, but wanted to contain everything in one go here. Two questions. Can we test heavy oil PVT? Can you talk about the limitations of the system?
Yeah. Again, heavy has a wide basically range in terms of viscosity or API. Basically, it really depends how you want to define the heavy oils. But particularly in our development, we tested oils from API of around 18 up to 40 plus, up to volatile oil samples. And the viscosity at reservoir condition, it was around 6 centipoise and below. Again, there are some challenges if you want to do very heavy oil system here, especially those which are so viscous, because the very viscous oil system, we may not be able to make those clear oil slugs in water. But the majority of the oil reservoirs that basically have even under 20 API gravity, we are able to test those in our system.
Yeah. And then a common question we get is observing the confining effects on phase behavior, such as saturation pressure when the channel sizes get small.
Yeah, the short answer is yes. As we confine the media, we change these thermodynamic properties. Again, but you need to be really, really small in order to suppress the saturation pressure. We tested in some cases where basically the size of the confinement was sub 10 nanometers. We saw a really huge suppression in the bubble point and dew point. But for conventional reservoirs, or as long as you are above hundreds of nanometers scale, you don't see that suppression in saturation properties much. But in short, yes, it can be suppressed if you go very, very small.
Yeah, and to give some context, the sizes of our channels, that I've been showing you today are between 5 and 50 microns. And the area where we start to see changes in PVD properties are sub 100 nano typically. And so there's many orders of magnitude size difference here between these systems, and our system behaves as bulk. All right. So I'll keep going here. There's a question about GOR, GCR measurements in the future. Ali, do you want to opine upon that?
Yeah, I mean, again, it'll tie to the Sapphire Lab application. I guess we'll talk in last, but in short answer, in our lab at this point, we don't measure the compositional analysis and the GOR, because we have to run a single stage flash in order to get the composition of oil and gas, and then to recombine them to get the recombined composition, and also measure the GOR. So we can have those measurements done in collaboration with some well-known service labs out. But for the on-chip recomp, which is really important to have the composition, we just need to measure the composition of the in basically feed components. I mean, your gas and oil, and the rest you can basically measure the composition using the material balance.
So for miscibility, this is a slightly older measurement, one of the first PVT measurements we fully commercialized. We were working with Equinor at the time, and Tao Yang, a good colleague of ours at Equinor, came to us and said, I love miscibility studies, but I hate slim tubes. Can you solve this problem for me? And so we did. We worked on it for about 9 months to develop this method that delivers a minimum miscibility pressure with a pressure point every 15 minutes and basically an MMP per day with plus or minus 30 PSI accuracy. So what we've done here, again, we're going to rely on some cartoons to illustrate what we're doing, but we're detecting miscibility by observing the gas and oil inside of a porous media that replicates the same physical characteristics as your standard slim tube. And then we're also measuring oil production near the exit of the slim tube. So we're looking at how the displacement process happens. We're also in the process visualizing how a displacement front develops, if it develops, in all cases. So what that actually looks like is on the left side here, we have an immiscible case. We've got a slim tube filled with oil that we're now injecting CO2 into. And we can see very low production of the oil, sharp solvent oil interfaces, and very lots of oil left behind. This is a very clearly immiscible case. When we move over to a miscible case, we can see when we start the measurement, we have lots of oil that's being retained. But what hasn't happened yet is a lot of contact between the gas and the oil. And so through the experiment, we see the gas and oil mix together, and we actually see the miscible front develop. Our measurement is then stopped as soon as we have breakthrough. So at the end of breakthrough, where we have all the oil front passes, approximately 1 pore volume, we're now looking at 0 oil remaining in situ. If we run this experiment a few times, and by a few, I mean, 20 to 40, what we're able to do is plot out recovery as a function of pressure. And you can see if we zoom in right at the minimum miscibility pressure here, this is a statistical process. And so in some cases, you have very high recovery, but it is not miscible. And we know that it's not miscible because if you repeat the experiment, we have high variability in that recovery. In our case, when all cases are produce above 99% recovery near the exit of the slim tube, that's a miscible case for us. And so it really does show that miscibility is developed. It's not a light switch, but there is a very clear differentiation when you reach that miscible pressure. We've now done, this has been in the market for about 3 years, and we believe Interface has run more MMP testing in the last 3 years than the rest of the industry did in about the decade before that in terms of a sheer measurement volume. We're really proud of these measurements. You can see how they compare here. But if you've seen our data before, then you've seen this plot. But what is new is you haven't seen a new study that was completed last year and published at ADIPEC in Abu Dhabi this year, which was looking at CO2 and the impurities that are found inside of industrial CO2 and how they impact minimum miscibility pressure. Ali, do you want to walk us through we did this is a partnership with a client here in Alberta.
Yeah, I mean, again, the whole point here is to look at the change in the CO2 MMP as a function of different gas impurities. I mean, on the table, you can see the type of impurities. We have recycled gas, which is basically a mixture of CO2 with different hydrocarbons, and then some pure impurities, including C1, nitrogen, hydrogen, argon, and H2S, and also in a binary and ternary mixture as well, trying just to have more sensitivity if you have multiple impurities altogether. I mean, the right table here just shows some data that was taken using the slim tube and also the microfluidics, just to ensure that we can match the previous data. Their slim tube data is not 100% complete here, but they ran it at two pressures, 126 and 127 bar, and then the recovery is again plus 95%, which is miscible. In our case, we tested at two pressures, 133 and 123, and we got 99% displacement efficiency, which again shows the miscible. So we ran these comparison just to show that we still can match the previous data on the pure CO2. And yeah, the next slide is the actual data. So here, the table you see, you can see if we change the impurity, how much change we get on the MMP. In some cases, we are still fine. For example, 5% methane impurity, we are still miscible at reservoir pressure. But if you pass 5% and go to 10% or 15%, your MMP actually goes above the reservoir pressure. So operationally, you are not able to inject CO2 at miscible condition when your C1 impurity goes beyond, let's say, 10% or so. The same goes for argon, for example, 2% argon, you increase the MMP above the reservoir pressure. And you can also get some idea how these impurities impact the MMP. For example, H2S, yeah, it's been reported that it can reduce the MMP. And you can also see basically when you have, for example, 7% methane, but with 2.5% H2S, there's a combat between C1, which increases the MMP, and H2S, which reduces the MMP. And in the end, you are still in the miscible zone. Again, we ran 18 tests. And if you want to include, and for each of tests, we ran at least 20 data points. So you're looking at 360, 400 slim tube equivalent runs, and we ran all of those experiments in less than 4 weeks, which is, I guess, it's a world record. But yeah, this is how fast and throughput this basically product is in terms of giving you the miscibility data for any gas feed.
As far as we know, this is the largest industrial miscibility study that's ever been performed. And we did it in less time than it takes to run one typical slim tube. So we were obviously very happy with this, and so was the client. So the last thing I'll show here is sort of a sensitivity chart here, and some conclusions on this is that, CO2 is never pure in an industrial setting, especially when we're in a recycle situation and you get there's just a lot of factors. And so it is important to understand sort of operating limits for these fields. But the ability to actually make these measurements is pretty reasonable. So if you take the time and cost to do a couple of slim tubes versus to get this full data set, you'd be in a similar range. So it's a much larger, richer data set overall. So with that, I'll conclude on today's presentation of our Interface's new PVT measurement capabilities. we're really excited by the opportunity that this presents to the industry, not just in terms of short term, which is getting more data from traditional methods and getting a higher level of confidence in your PVT, but long term, working with our clients to develop these new workflows that become available only once you have a system that has reduced the bottlenecks. And by de-bottlenecking, our goals are to be offshore on well sites all over the world as fast as we possibly can. So with that, I'll say thanks and open it up for any questions here. And I'll start. We've got an anonymous question here about nitrogen impacting miscibility. Ali, I have my answer, but I'm curious what you would say here.
Well, in general, nitrogen, if you want to add it to, let's say, CO2, it'll increase the minimum miscibility pressure. And pure nitrogen, again, it has a very high MMP. But again, you need to test it, but typically nitrogen increases the MMP of the CO2 if it's supposed to be mixed with CO2.
Excellent. Well, I don't see a lot of other questions coming in. I will put this out here. We're looking forward to validating this for everybody. As I said at the beginning, Interface's philosophy is show, don't tell. So if you're working on PVT today, if you've got PVT sensitive processes, we'd be more than happy to come in, demonstrate our capability, and work with you to give you the confidence in our system that we have by making those measurements and doing it as efficiently and cost effectively as possible. So with that, I will sign off here and say thank you very much, and we'll speak with you all very soon, hopefully. I'm going to play a video at the end of the presentation here just to let it play and let questions come in as people sign out. So thank you very much. Have a great day. And if you have any other questions or comments, please feel to email me, call me, or watch this again on YouTube once it gets posted. Thank you. As we're going here, I see a few questions coming in. Is the system available in the market? Yes, Sapphire Lab is available. We've got the first units were delivered about a year ago, with the first PVT units being delivered in 2024. So yes, we're available to deliver anywhere in the world, whether the service companies or oil companies. Asphaltene onset pressure. It's a big topic. Ali, do you want to talk about AOP for a bit here?
Short answer, yes, we tried AOP. In some cases, we could get the AOP, but in some cases we couldn't. But I just want to remind you that, if you want to do a comparison on the AOP, we have to ensure that the samples are exactly the same, and the AOP has been measured on the same sample that we're going to test. At the same time, we believe that there are some limitations that may not be able to detect the AOP if the amount of the onset of the asphaltene is pretty small. But again, it needs to be explored further, but we can definitely try that. Yeah,
basically the summary is we see asphaltenes on our chips regularly. We see them come out as a function of pressure. When there's low asphaltene content, it becomes difficult to quantify that measurement. And so there's more work to be done on that in order to really get it to a commercial state. I'd say it's in sort of a prototype state right now. We do a lot of work with asphaltene inhibition chemistry, wax inhibition chemistry. So a lot of flow assurance sort of solids questions. As long as the asphaltenes are already destabilized and we're looking at things like particle size and deposition, that's something we do regularly. So I would put that in a different category than asphaltene onset pressure that we do work on quite often. Thank you for the question, Hakim. One more question here. Do we have a presentation on chemical EOR applications in the future? We do. You can go on our YouTube channel today. We've got actually 2 webinars on chemical EOR there. And then we're always available to basically hop on a call and chat with folks about their specific needs. But yeah, chemical EOR is something we do. Again, it's a big part of our business. It's something we do all the time. And we published a paper, 2 papers this year on chemical flooding, both in very heavy oil applications as well as in sort of a more model laboratory situation. So I'm happy to share those papers with you. Excellent. Thank you very much, everybody. We'll speak with you all hopefully very soon. Have a great day.